Good morning, students. Last time we have completed with group 16. Now today we'll be starting with the group 17 part. Now with respect to the group 17 part, what we can talk or what we can discuss over here is first of all group 17, or we also call it as group 7A of the P block or of the periodic table what we have. This is called the halogen family. Okay. Now for this halogen, let's understand exactly how it is. Now with respect to the halogen part, first over here, all right. Now, why do we call group 17 elements as the halogens? The word halogens comes from the word halos. Halos means sea salt and genes means producers. So basically, sea salt producers is what we call as halogens. Now, what are these halogens? Fluorine, chlorine, bromine, iodine, astatine and tennessine. So we have total 6 halogens: fluorine, chlorine, bromine, iodine, astatine and tennessine. Last two elements, astatine and tennessine, these are radioactive elements. So they have short half-life periods. Hence in the discussion, it will be only fluorine to iodine what we talk. Okay. So this is called group 17. Why? Because there are 7 electrons in its outermost shell. General electronic configuration of halogens is Ns2Np5, 2 of the S and 5 of the P. Now, first of all, let's understand how do we remember this. Okay, I want everybody please in a book somewhere write down. I'll give you the mnemonic what I have made for this for group 17 elements. Write down for the halogen part. Fast clouds break in Atlantis and Tennessee. Fast clouds break in Atlantis and Tennessee. Now fast, fluorine, clouds, chlorine, break, bromine, in, iodine, Atlantis, At, astatine and Tennessee. Tennessee is tennessine. The last element, Tennessee, is basically Tennessee is one of the US states where the laboratories were there. So that's why the credit is given by the IUPAC with respect to the place where these laboratories were there. That's why the name tennessine. So that's the group 17, what we have as the halogens. Now important, atomic number wise. How do we remember the atomic number? Please write down on a paper. F, Cl, Br, I. Then astatine is capital A and a T. And tennessine is capital T and a small s. Now as usual, atomic numbers we know. Fluorine, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So fluorine is 9. Now for chlorine, you will add 8 to it. So 9 plus 8, 17 is chlorine. Now to this chlorine, you will now add 18. So 17 plus 18, that's going to be 35. That's the atomic number of bromine. To bromine, again you will add 18 over there. So 35 plus 18 if I do, then that's going to be 53. That's the atomic number of iodine over there. Now to this iodine, I will add 32. Is clear? So 53 plus 32. So that's going to be 85. That's the atomic number of astatine. And for the last element, tennessine TS, again I will add 32. So 85 plus 32. So that's going to be 117. That's the atomic number of tennessine. So the addition goes 8, 18, 18, then 32 and 32. So 8, 18, 18 and then 32, 32. That's how we remember the atomic numbers part. Okay, so that's the halogens. Let's see this now. What exactly is 7? Everybody please come on the slide over here. Halogens are generally what we call them as, they are highly reactive non-metallic elements, because we all know across a period from left to right, metallic character decreases, non-metallic character increases. So halogens are the most non-metallic elements. Is it clear? That's one. Now last part people, what is 7 over here? Astatine and tennessine. These are the ones which are radioactive substance. That's why in the discussion they will not be there due to short T-halves. That's the half-life that we have discussed. Shorter the T-half, more harmful is the substance. Now with respect to the occurrence part, fluorine occurs mainly in the form of what we have as fluorides. So that is fluorspar, CaF2. This is also called fluorite. Please add one more name and keep. CaF2, it's a name of an ore. It is called fluorspar or fluorite, Fluorite. Then cryolite, that's Na3Al F6, that's also an ore of aluminium. And fluorapatite, we discussed this. That's 3 moles of calcium phosphate dot CaF2. Then seawater mainly contains all the halides over there, where sodium chloride is mainly present in the seawater. Please look at that, 2.5% by mass. If you recall, what is 2.5% by mass? Weight by volume, 2.5 grams per 100 ml of water. That's the concentration of sodium ions in seawater. That's the part. Then sodium chloride also, and one more name is there, one more carnallite, that is KCl, MgCl2 with 6 water. Then the seaweeds which contains iodine over here, and then chilled saltpeter. Now, if anybody recalls, what was exactly chilled saltpeter? Sodium nitrate, NaNO3. That's called chilled saltpeter. And if it is Indian saltpeter, that is potassium nitrate. It contains around 0.2% of sodium iodate. Sodium iodate is NaIO3. Alright, that's one where iodine is a +5 oxidation state. Then tennessine is a synthetic radioactive element. Atomic number 117. We all have to know for tennessine, everybody, only the atomic number. So for all the elements till now, what we have done, the new elements coming in 15, 16 and this 17 now, it's only going to be the, what we have is nothing but the configuration, that is radon. Then it is 5F14, 6010, 7S2, 7P5. NS2NP5 is common. Rest is the F and the D part. Alright. And it says the half-life is only milliseconds. So if it is milliseconds, matlab it is most harmful. Alright. So discussion FClBrI. That's the group 17 or old form of periodic table. It's also called group 7A. Roman number 7 and capital A. That's the old part over there. Now people coming to the property. 2-3 abnormalities are there. I want everybody, please keep a pen and paper and write it down. So atomic number, mass number, all this is okay. Look at that important one, abnormal part, electron gain enthalpy. That is what we have to do. We have done this in periodic table also. Once again, everybody, no values. Okay, just the orders. What is electron gain enthalpy? Energy released when an extra electron is added to the outermost shell of a free gaseous atom to form its anion. So that's why that negative sign, because that's the enthalpy change, delta H value. Now technically F should be maximum, but the order is Cl greater than F, greater than Br, greater than I. Why? Because fluorine has a small size, 2,7. 7 electrons in the second shell. Capacity is only 8 electrons. So the incoming electron will experience repulsion from the existing 7 electrons. That's why we say its electron gain enthalpy of F is less than Cl. Cl also has 7 electrons, 3s2, 3p5, but it is the third shell, not the second shell. So as for F, it is the second shell. It has no vacant d orbital, but Cl has vacant d orbitals. That's why the electron gain enthalpy of Cl is, Cl will have more tendency to gain an electron as compared to F. So the energy released is more. So remember the order. Please write it down. Electron gain enthalpy order: Cl greater than F, greater than Br, greater than I. Then electronegativity, people, as usual, as one goes down the group, atomic size increases. So ionization enthalpy, electron gain enthalpy and electronegativity, all the three will decrease down the group. So on the top we have F, that's the maximum value of 4 units on the Pauling scale, and then it decreases. Then this is important, people, delta H, that's written there, hydration, matlab the hydration enthalpy, what is there? That is when 1 mole of a substance is dissolved in water, then the heat which is liberated. Now if you observe, for F the enthalpy of hydration is very, very high, 515 kilojoules per mole. Then as it goes down, it decreases. So F has maximum, meaning fluorine when dissolved in water, it readily forms fluoride ions. So you can link this to your redox. If it readily gets converted to fluoride ions, matlab it undergoes reduction. If it readily undergoes reduction and liberates a large amount of heat, means over there, what do we say? It is the strongest oxidizing agent. That's why in the SRP series, fluorine is kept at the top of the series over there. So that's the part. That is one hydration enthalpy concept, what you have to know. Second, people, melting point. As one goes down, melting point and boiling point will increase. Then density, people, if you observe, yes, density is increasing as one goes down. What is the reason for the density to increase? Please specify somewhere. The density is due to agglomerization. AGGLOMERISATION. Agglomerization. What is exactly agglomerization? Agglomerization is basically over here the molecules which come closer. So many molecules, when they come closer, that tendency is called agglomerization. So as one goes down the group, the molecules come closer, because of which we say that's called agglomerization. So the density increases. So that's the reason. One. And now something again very abnormal, bond dissociation enthalpy. Amount of energy supplied to break a bond to form free gaseous atoms or radicals. As one goes down, what should happen, people? Technically, the value should, over there, nothing but technically the value should become lesser, because the size becomes bigger. Size is bigger, then the bond length will be greater. Larger the bond length, less the bond enthalpy. So maximum value should be with F, but the order is again like electron gain enthalpy, but not same like electron gain enthalpy. An abnormal order. What is the order? Chlorine Cl2 greater than Br2, greater than F2, greater than I2. So totally different order. Please specify this, important. Bond dissociation enthalpy order is Cl2 greater than Br2, greater than F2, greater than I2. So look at that. You have the values wise, Cl ka value is more, chlorine is more. Then we have bromine, then we have fluorine, and last we have iodine. What is the reason for this? People, in fluorine, it is in the second shell, no vacant d orbital, most electronegative element, 7 electrons in the second shell, so there is inter-electronic repulsion, because of which its bond dissociation enthalpy is lesser over there. So that's the reason part of it. Okay, so this is the abnormal part, and then comes the last part, everybody, E naught values, that is the electrode potential value. People, we all know in the SRP series, what is the order? FClBri, matlab fluorine, then chlorine, then bromine, and then iodine. So as they are placed in group 17 in the periodic table, same way are their electrode potential values, where fluorine on the top having the highest SRP value, all have positive values. Maximum is fluorine, which indicates it is the strongest oxidizing agent, readily undergoes reduction. So that's the value part. Okay, that's one. Next, people, moving, we have now, we'll talk about these properties. Electronic configuration, people, all have NS2 NP5, meaning 7 electrons in the outermost shell, that is one shot of the noble gas. People, what about the atomic size? Across a period from left to right, atomic size decreases. So halogens will have the smallest size. Alright. What about the inert gas? We all know inert gases have slightly larger size than the corresponding halogen because of electron-electron repulsion. So halogens have the smallest size, means they readily undergo reduction, and they are non-metals, and all are oxidizing agents. So that's the part over here. That's one. Then I values, yes, as one goes down, people, shells are more, so I value will decrease as one goes down the group. Then electron gain enthalpy, I told you, it's an abnormal order because of the inter-electronic repulsion. So that's the whole part what is given there. It's a negative value, and recall, energy is released, where two important part about electron gain enthalpy from periodic table. What is that? Oxygen, we did in group 16. Oxygen ka second electron gain enthalpy is positive. Dusra, inert gases have positive values of electron gain enthalpy, because when you add an electron, it jumps to the next high energy level, because of which energy has to be supplied. Okay, so that's the part. So that's the reason over there, there is strong inter-electronic repulsions, and because of the repulsion, in the small 2p orbitals of fluorine, the incoming electron does not experience much attraction. That's why, people, we say tendency is less. And remember, fluorine is also considered to be a super halogen. Most electronegative element having a value of 4 units. No vacant d orbital, 7 electrons in the second shell, gains only 1 electron, has only one oxidation state of -1 only. That's about fluorine, which makes it a super halogen. Then electronegativity, we discussed that decreases as one goes down. And next, halogens have maximum negative electron gain enthalpy in the respective periodic table. People, we know this part over there. What is the reason for them to have maximum? Because of the small size. Alright, so because of the small size, nuclear pull is more. So when electron is added over there, energy released is more over there. Okay, that's the part over there, because they try to achieve the noble gas configuration. So that's the one part. Then comes, people, the physical properties. Fluorine, chlorine are gases. Bromine is a liquid, and iodine is a solid. And all these halogens, they have color because they absorb light in the visible region. So fluorine, pale yellow gas. Chlorine, school mein padha hoga, greenish yellow gas. Bromine, reddish brown liquid. And iodine, that's a violet solid. Okay, so that's the part over there, first there. Melting and boiling point will increase as one goes down. Then absorption of UV region. Then the colors are given. Fluorine, that's yellow, pale yellow. Chlorine is greenish yellow. Bromine is a liquid, that's reddish brown, and iodine is a violet solid over there. Then it says fluorine, chlorine, they react with water because of its high hydration enthalpy. Fluorine has maximum. Bromine and iodine are only sparingly soluble, but they are soluble in organic solvents. Then, people, important point, what I had explained, again they have given here, look at that. One curious anomaly is there. The smaller enthalpy of dissociation of fluorine as compared to Cl2. I told you the order. Bond dissociation enthalpy among halogens, Cl2 greater than Br2, greater than F2, then I2. The reason is over there, the trend is like this. It's chlorine, bromine, and then iodine part. In fact, it's chlorine, bromine, fluorine, and then iodine. And that's because of the large electron-electron repulsion. That's the issue over there. Clear, everyone? How is this? Okay. Then. Now, see what it says. Although electron gain enthalpy of fluorine is less negative as compared to chlorine, fluorine is the strongest oxidizing agent than chlorine. Matlab, in spite of Cl, chlorine gaining an electron more as compared to fluorine, still fluorine is the strongest oxidizing agent. Why? Two reasons. Low enthalpy of dissociation. People, I told you the order right now only. Cl2, Br2, then F2, and then I2. And second, high hydration enthalpy to form F minus. These two reasons make it the strongest oxidizing agent. Mark this question important. Okay. Now, coming people to the chemical properties, the first part we're going to talk about is oxidation states. Now listen carefully. We all know what's oxidation state? The net apparent charge assigned to an atom in its compound. That's called the oxidation state. Now all halogens, normally it's NS2NP5. So all have a common oxidation state of -1 and a common valency of 1. But apart from -1 is shown by all, but only F shows -1 because of no vacant d orbital. Cl, Br and I, apart from -1, they also show +1, +3, +5 and +7. Why? In there, because they have vacant orbitals. So we have the first excited state, second excited state, and also the third excited state where we can have more unpaired electrons. So we will see in the compounds like interhalogen compounds are there, where in interhalogen compounds between two halogen atoms, we will see how the bondings are there. So remember this, F shows only -1, Cl, Br and I apart from -1 also show +1, +3, +5 and +7. So that's the part. So look at this part. This is in the ground state, 1 unpaired electron. Then first excited state, people, this has got 3 unpaired electron. Then second excited state, it has got 5. And then comes over here after the second comes the last. Now here there's a mistake over there actually. They have shown 2 electrons. Technically there should be only 1. So 1 over here and the remaining is. So total 7 unpaired electrons. Please understand this is the mistake, okay? There should be only 1 unpaired electron. That's 1. Now what it's trying to say, just see this part. Higher oxidation states, yeah, because of the presence of, they are in combination with highly electronegative atoms like fluorine and oxygen atoms. That's in interhalogen compounds. They are oxides and oxoacids, like how we have done phosphorus oxoacids and sulfur. Same way chlorine also will have oxoacids. Interhalogen I told you, between two halogen atoms. And they are oxides like chlorine monoxide, chlorine dioxide, chlorine hexoxide and chlorine heptoxide. We'll be seeing that. So in the oxides also we see the state. Acha. Bromine and chlorine also show in some place +4 and +6 oxidation state also in some of the parts. Alright. Now being most electronegative, it exhibits only -1 oxidation state. Clear everybody, oxidation state concept? Okay. This one correction, okay. This is only 1 unpaired electron. Alright. Next people, now the logic understanding, okay, what is happening. It gains an electron, so fluorine is the strongest oxidizing agent. I want everybody, I'm explaining some SRP series point. Please see the slide carefully. Now what it says, now the order is what way? Fluorine, chlorine, bromine and then iodine. So look at that part. If I have these two, fluorine and chlorine, who will be oxidized and who will be reduced? If anybody remembers, I explained in the redox part, diagonal rule. What was the diagonal rule? Nothing to do with diagonal relationship, people. Diagonal rule. In the reduction half, the one having lower SRP, not of fluorine and chlorine, who will have lower? Chlorine. the species on the right hand side, that is this chloride, okay, that will readily get oxidized. Matlab the backward reaction will take place, so chloride will become chlorine. And above, the one having more SRP in its reduction half reaction, see on the slide, the species in the reduction half on the left, that is fluorine, will readily get reduced. So that's the diagonal rule what I was talking, fluorine and chloride. So chloride gets oxidized to chlorine, fluorine gets reduced to fluoride. So what is the body language? How do we talk? If chloride is oxidized to chlorine and fluorine is reduced to fluoride, we will say fluorine displaces chlorine from their salt solution. So when I say fluorine displaces chlorine from their salt solution, fluorine itself will get reduced and chloride will get oxidized to chlorine. That's the diagonal rule. That's what you see. Now bromine and iodine. Who's above? Bromine is above. So left hand side reaction, left to right will happen. Bromine will get reduced to bromide and iodide, which is down, will get oxidized to iodine. So again the diagonal rule. Alright. Then now for people, it is the strongest oxidizing agent. How do we calculate? Now because we have done in thermodynamics, thermo depends on numbers. So it's a summation of 3 enthalpy changes which explains, okay, which is a good oxidizing agent. Please look at that. One is all halogens, people we all know, X2, fluorine, chlorine, bromine, iodine. Chemical bonding, VBT, all are formed by PP axial overlap. So there is a single bond, that's a covalent sigma bond. It's a PP axial overlap. So first the halogen molecule splits into its free atoms, that's called its dissociation enthalpy, that's half. Then in the gaseous state, it gains an electron, so that's called electron gain enthalpy. And then in the gaseous state, then it combines with water to form its ions in the aqueous state, that's called hydration enthalpy. So it's a summation of 3 things: bond dissociation enthalpy, electron gain enthalpy and hydration enthalpy, which tells us over there where the summation of all the 3, lower the value of all the 3, meaning more tendency to form its ions over there. That's the part. Okay. So this can be illustrated over here. Look at this part. Fluorine oxidizes water to form oxygen. So look at that. Fluorine with water gives you over there. Fluorine gets reduced to fluoride and water, may say oxygen, is released over there. That's one. Then same way as basically it says halogens, other ones, that is chlorine and bromine, they react with water and they form over there nothing but its corresponding hydrohalic. Matlab suppose I take it as chlorine. So chlorine plus water will give us HCl, that's hydrochloric acid, plus HOCl, hypochlorous acid. We have done. What's hypo? Lower oxidation state. So in HOCl, Cl is in +1 because oxygen is -2 and hydrogen is +1. So hypochlorous acid, that way. Okay. And last part about iodine. Iodine with water, the reaction, the reaction of iodine with water, it says, is non-spontaneous. Matlab it won't happen on its own. In fact, iodide can be oxidized to oxygen in an acidic medium. So iodide will get oxidized to iodine and H plus ions will get reduced to water. So remember the diagonal rule part, that's an important point. And summation of 3 enthalpy changes gives us the concept who's a good oxidizing or a reducing agent. Okay, that's one. Then important now, people, today we are going to only talk about the periodic functions. Next class we'll start with respect to the halogen compounds. Okay. Now this part is very important. Please concentrate. Like we had anomalous behavior of nitrogen for group 15. Group 16 was oxygen. 17 is fluorine. This is a definite question to come. We'll just discuss the points. Okay. 1. Fluorine, for example, we say over there, it differs because of 1, ionization enthalpy, then electronegativity and enthalpy of bond dissociation, and electrode potentials all are higher for fluorine than the expected, because fluorine has 7 electrons, so higher ionization enthalpy, electronegativity 4 on the Pauling scale, enthalpy of bond dissociation when I am talking over there, that's 1, and second it's electrode potential values placed on the top over there. Okay, that's 1. Then ionic and covalent radii, melting point and electron gain enthalpy are quite low than the expected. We know electron gain enthalpy is the abnormal order. And the reason for it is, why does fluorine show this exceptions? Because of its one important point, its small size. highest electronegativity, and low FF bond dissociation enthalpy, and non-availability of vacant d orbitals. You have 4 points, always remember. Strongest oxidizing agent, most electronegative element in the entire periodic table, low FF bond dissociation enthalpy, and no vacant d orbital. That's why we call fluorine a super halogen. That's one. Then its reactions are highly exothermic because hydration enthalpy is higher. So it readily gets converted to its fluoride. That's why it says the reactions are exothermic. It liberates heat. Then it forms only one oxoacid. Is this clear? When it combines with over there with oxygen, we say fluorine will form only one oxoacid, that is called HOF, and that HOF is called hypofluorous acid. Something important, please make a note. HOF, fluorine forms only one oxyacid, hypofluorous acid, where if I ask a question, what is the oxidation state of oxygen? Answer is 0. Hydrogen is +1, fluorine is always -1, so oxygen here will be 0. So remember, only one oxyacid it forms. Then, whereas other halogen will form more oxyacid. And important point, hydrogen fluoride, that's basically one of the hydrides of fluorine. That is a liquid at room temperature as compared to other hydrogen halides. So make a note, reasoning question. I've discussed this earlier. HF is the only liquid at room temperature. Other hydrogen halides, HCl, HBr, HI, all are gases at room temperature. What is the reason? Same. Strong intermolecular hydrogen bonding. So due to strong intermolecular hydrogen bonding, we say HF is a liquid. That's the part. That's the hydrogen bonding concept. Then with hydrogen people, it combines to form its hydrohalic acids. Very important people. Acidic strength. We have done an ionic. People who will be a strong acid, HF or HI? Always HI. HF bond is very strong. So will a strong bond easily break? No. So HF will give least H plus ions. So be clear. Whenever they say acid strength, it is with respect to who gives H plus ions fastest in water. So that will be HI. So HI is the strongest acid, HF is the weakest acid. But if I talk in terms of bond enthalpy, HF bond enthalpy will be maximum because difference in electronegativity. Greater the difference in electronegativity, more is the bond polarity, and higher the bond polarity, more is the energy supplied. So be clear. Bond strength wise, HF is the strongest bond. Acid strength wise, who gives H plus faster? HI will be the strongest acid. That's what is given there first. Please make a note of this. The acid strength, HF, HCl, HBr and HI. And stability of these halides will decrease down the group. Why? Because of the decrease in its bond dissociation enthalpy. Size is bigger, no? So, but obviously the bond dissociation enthalpy will be, over there, the energy required is less to break and stability is also less. So, if a question comes in terms of stability, then HF is more stable as compared to HI. So, be clear. Acid strength, HI is more. Stability wise, HF is more stable. So, now here we have given the same values over here, the melting boiling points. That's one. Then the boiling point of HF, look at that. Boiling point of HF is greater as compared to the other ones. The reason is same, intermolecular H bonding. That's one. Then bond length wise it's fine. Then dissociation enthalpy and P of K value. People look at that. HF P of K. People, we know about P of K. What is the formula? P of K is minus log of Ka to the base 10. So larger the value of K, lower is the P of K, and lower the P of K, stronger the acid. Now all of them have negative values of P of K, matlab they are highly strong. This has a positive value. So that's why it's a weak acid. Clear everybody? Okay, that's one. Then next is people, its reaction with oxygen. Here people, it forms a variety of its compounds. So look at that. It forms two oxides, OF2 and O2F2. Oxygen difluoride gas and dioxygen difluoride gas. Now OF2, only compound where oxygen has an oxidation state of +2 because fluorine will always be -1. So important, make a note. Shape of OF2 similar to water molecule, O and the 2 fluorine, like water, O and 2 hydrogen. So it's a bent or an angular geometry, distorted sp3 hybridized. Okay. And second is O2F2, that's dioxygen difluoride, where each oxygen is in +1 oxidation state. So normally oxygen is always -2, that's oxides, -1 for peroxides, +1 for dioxygen difluoride, and +2 for oxygen difluoride gas. OF2 was also with respect to VSEPR in chemical bonding. Okay. Then it says only OF2 is thermally stable. Okay, so out of the two, only OF2 is the one which exists at room temperature. Then oxides are formed over there, where see there, both are strong fluorinating agents, where people now important uses, see this part. O2F2 oxidizes plutonium to plutonium hexafluoride, and the reaction is used in removing plutonium as plutonium hexafluoride from spent nuclear fuel. So nuclear reactors, the material which is used, that's the plutonium compound. So in that it is used in removing plutonium from plutonium hexafluoride, that is O2F2. Chlorine, bromine, they form oxides, basically staining from +1 to +7, which I told you. -1 for only for F. But ClBrI, apart from -1, they will show positive states of +1, +3, +5 and +7. And also in some oxides, Cl and Br will show +4 and +6. That is one. Then, the next part we have, people, what we have to talk now is about the different oxides it forms. Now, what exactly are the oxides that it forms? Now the oxides it forms over there, observe this carefully. What is given over here? A combination of kinetic and thermodynamic factors leads to the general decreasing order of stability of oxides. So iodine, the oxides are more stable than chlorine and bromine. Then it says higher stability of oxides of iodine is due to, people mark this point important, stability of oxides of iodine is more, it says, because of due to greater polarizability of the bond between iodine and oxygen. Polarizability, I'm sure everybody remembers, if you recall properly, what was exactly polarizability? Tendency of an atom's electron cloud to be distorted from its usual shape by an external electric field. Matlab here what is happening? Bond is between iodine and oxygen. So oxygen is electronegative. So it will try to pull. So the electrons of iodine of the valence shell, they are being distorted or pulled in one direction because of an external electric field over there. And that is called as polarizability. Okay. So because of that, we say the stability of iodine oxides is more. So for MCQ point. Okay. Chlorine can form multiple bonds over there because of the vacant d orbitals, where it says the increase in stability of bromine lacks because of characteristics to form. Hence, stability of oxide, it says the increase in stability, bromine lacks both characteristics. Hence, stability of oxide of bromine is least. Matlab in bromine, generally, we will see +4 and +6. But it says, what happens over there? Chlorine can form multiple bonds. Bromine is not able to form multiple bonds. That's the reason why it says, and plus polarizability is lesser. That's the reason, because it's less electronegative. That's why it says stability of bromine oxide is less. And mainly chlorine ke oxides are more stable. So look at this, people. Chlorine forms oxide. I'm giving you the name of all these compounds. We're going to talk about it. Cl2O. Chlorine monoxide. Cl is oxidation state +1. ClO2. Chlorine dioxide. Cl will be +4. Cl2O6. Chlorine hexoxide. Chlorine is +6. And Cl2O7. Chlorine heptoxide, where chlorine is +7. Clear? Where important uses ClO2, that's chlorine dioxide. That's a bleaching agent for paper pulp and textiles in water treatment. Bromine also forms oxide, Br2O, BrO2, BrO3, and are the least stable halogen oxide. That's called the middle row anomaly. Now, what exactly is the meaning? Is this clear? And they exist only at low temperature. So people mark this important. Bromine forms 3 oxides, Br2O, is this clear? BrO2, BrO3, and are the least stable halogen oxides. That's called the middle row anomaly. Now, middle row is basically what? If you observe that the 3D orbital, basically, if you see over there, what I can call, we have done in structure of an atom, if you remember the concept of nodes. Okay, there were 2 types of nodes. One was an angular node and one was a radial node. Angular is in between, that is what we call as the flat plane, between the flat plane, that's the angular node. But if you recall structure of an atom, formula for angular node was L. Okay, L means the azimuthal quantum number. And second were the radial nodes, those are the spherical nodes which are there. That formula was N minus L minus 1. Alright. So what is observed with respect to bromine? If we see bromine configuration, the 3D is complete. 3D10 we write. If you see OVA with respect to bromine, atomic number 35. So it's basically, if you observe, argon, then after argon we are having straight away over there nothing but 3d10. After 3d10 we write over there as 4s2 4p5. So the 3d orbital, if you say, please pen it down. 3d, if you calculate the radial nodes, 3d, n minus l minus 1, so n is 3, l for d 0 1 2, so 3 minus 2 minus 1, so that's 0. So I can say for the 3d orbital the radial nodes are 0 over there. And what happens, and hence they have, they come, what I can call, they will have a tendency to come close to the nucleus, because if there is no radial nodes it will come more nearer to the nucleus. And second, we can say, if you look at the 4p orbital, because that is 3d done now, 4s2 4p5, so 4p. If you take 4p, 4p will have how many radial nodes? 4p may n is equal to 4, l will be 0 1, so 4 minus 1 and again minus 1, so it will have basically 4 minus 2, so it will have 2 radial nodes. So if it has 2 radial nodes, the transition of electrons, the movement of electrons, is this clear, between these two nodes, is this clear, will be not much, because anyway because it's a small gap what is there. So if the transition is going to be less, it does not show +5 and +7 oxidation state, it shows +4 and +6. This is what I call as middle row anomaly. So once again, it is because of what is middle row anomaly over here. 3d, no radial nodes over there. But if I talk about the 4p, it has got 2. So the transition of electrons will be lesser. That's why it does not show. Okay, and that's called the middle row anomaly part. Then second, iodine also form oxides and they are insoluble solids. And important people, I2O5, that's diiodine pentoxide. It's a good oxidizing agent used in estimation of carbon monoxide. So people, these uses will be important. So this is with respect to reactivity with oxygen. Then next we have people over here, this is the last part, reactivity with metals. Halogen readily form their metal halides, like magnesium combines to form magnesium bromides, where stability, if you say the ionic character, catch this word, ionic character of halides will decrease in the order. Metal fluorides will be more ionic, than metal chloride, then bromide, and then iodide. This is simple people, ionic bond formation. Fluorine, most non-metal and the metal, so the bond will be ionic. So the ionic character, metal fluorides will be more as compared to metal iodides. Now important, see this. If a metal exhibits more than one oxidation state, then the halides in the higher oxidation state will be covalent than the one in the lower oxidation state. So Cl, it shows +1, +3, then we have seen over there +6, +7 also. Now in +7 matlab what is happening? We have done this earlier also. Higher the oxidation state, more is the covalent character present. That's the Fajan stool part over there. So metal fluorides will be the most ionic, or most, we can see over there, the ionic bond will be strongest over there. But for covalent character on the same metal, if the oxidation state is very high, then there will be covalent character. That's the Fajan stool part. So see what it says. SnCl4, stannic chloride, tin is +4. Lead tetrachloride, +4. Antimony pentafluoride, +5. UF6, uranium is +6. They are more covalent than SnCl2, stannous chloride, +2. Lead chloride, +2. Antimony trichloride, +3. And uranium tetrafluoride, +4. So higher the oxidation state, more the covalent character, because Fajan's rule, charge by size ratio. Okay, so higher the charge, smaller the size, more is the polarizing power. And next people, reactivity of halogen towards halogen. It combines with another halogens people I told you. It forms a interhalogen compounds depending upon the first, second and the third excited state. So we have X dash, where over here if I have to talk over there, X dash corresponds to fluorine, because that's the one over there. So where X is the one, and it says, look at that, X is the larger halogen and X dash is a smaller. Small halogen is always fluorine. So like we can have ClF, chlorine monofluoride, X dash 3, ClF3, chlorine trifluoride. Then XX5, that is BRF5, bromine pentafluoride, and XX7, if you recall, IF7, iodine heptafluoride, sp3 D3 hybridized, pentagonal bipyramidal geometry, XX5 BRF5, distorted sp3 D2, that was an octahedral geometry part distorted there, that was one. So we can talk about it, what it is. And then it says fluorine exhibits only -1 state, whereas other halogen they exhibit +1, +3, +5 and +7. Why? All have vacant orbitals. So that's the part. Other halogens have vacant, but fluorine will not have. Now what it says, considering the parameters such as bond dissociation enthalpy, which is the less for fluorine, not the least is for iodine, electron gain enthalpy and hydrogen enthalpy, compare the oxidizing power of fluorine and chlorine. People, oxidizing power of fluorine and chlorine, who will be more? Any day fluorine will be more than chlorine. Why? Because bond dissociation enthalpy is less, but electron gain enthalpy of fluorine is also less. Hydration enthalpy of fluorine is very high over there, which makes it a better over there an oxidizing agent. That's one. Then examples to show the anomalous behavior of fluorine. People, anomalous behavior of fluorine will be one most important, no vacant d orbital. So only one oxidation state it forms, that's -1. Only one oxoacid it forms, that is HOF I told you, hypofluorous acid, where oxygen oxidation state is 0. No vacant d orbital, then you can say HF, hydrogen halide mein HF is the only one which is the liquid at room temperature. Rest are gases, HCl, HBr, HI, due to intermolecular H bonding. So you have many points, any two to be given there. And next it says C is the great source of some halogens comment. Yes, halogens, the word only has the answer. C, salt producers, and we discussed now 2.5%, 2.5 grams per 100 ml of water is the amount of sea salts, that is basically the sodium salts which are present in sea water over there. That's the reason why we say C is the greatest source of halogens. All right. With this, we are done with the first part, that is the periodic functions. Next lecture, we'll be talking about the compounds of it. Okay. Thank you, everybody. Thank you.